Good morning to those of you in the Americas. Good afternoon if you're in Europe and Africa, and good evening to those of you further east. My name is Steve Lewis, and I'm a Senior Director of RiskTech based in the UK. Thank you very much for joining us, and welcome to this RiskTech webinar, which is the fourth in our fourth series that we've run since May last year. The topic today is about reliability center maintenance and what it can do for you. Hopefully we can provide some useful and practical insights for you. Before we get going, if you've attended any of our webinars, you notice we upgraded to a more automated registration process. Hopefully you found that a lot easier to register for, certainly for more than one webinar at the same time. And we're also using Zoom rather than Skype for Business. I think because people do seem to prefer that. Quick spot of housekeeping. We've muted everybody. So the sound won't be distorted by any background noise. And if you'd like to ask any questions, then please use the Q&A function. So that's if you move your cursor down the page, then the Zoom tab pops up at the bottom, and there are a couple of speech bubbles that say Q&A. Click on that, type your message in. I'll keep track of all those questions during the course of the webinar, and then at the end, I'll cover as many of them as we can, and certainly within the 45 minutes we've got available today. Okay, I'd now like to briefly introduce RiskTech for those of you who don't know us. Apologies if you heard this 101 times before. I'll be pretty quick. So everything we do is around risk and safety management, particularly in sectors where the impact of loss is high. We've well over 300 people across 16 offices worldwide. We are part of TÜV Rheinland, who are a €2 billion provider of testing, inspection and certification services. We provide our services across 5 business lines: consulting, where we look to deliver proportionate solutions to help reduce and manage risk. We have online and classroom training, postgraduate education. We provide associates who will work at client locations to help fill resource and skill shortages. We also provide industrial inspection and assessments as part of asset integrity management programs. And we also conduct research and development in the field of risk and safety management. I'd now like to introduce our speaker today. Speaker is Dave Fiddler. Dave is a principal consultant. He's based in our Warrington office here in the UK. He's over 20 years of varied risk management and technical safety engineering experience, mainly in the civil nuclear industry in the UK, but also Central and Eastern Europe. So his clients include EDF Energy, Slovensky Elektron, and ČEZ, with a focus on maintenance optimization and supporting safety case submissions. This experience includes the application of RCM, which is Reliability Center Maintenance, and our topic today, identification of safety critical elements, development of performance standards, safety case production, safety reviews, HazOps, and hazard identification. So, I mean, Dave has a huge amount of experience. So really delighted Dave is here today to be able to give this webinar. So over to you, Dave.
Hello, ladies and gentlemen. You're welcome. It's a pleasure to speak to you today regarding what RCM can do for you. And today we're going to focus primarily upon how we can optimize the effort required to apply reliability center maintenance. But just to set a few kind of ground rules, that we'll look at a couple of the basics to begin with. First of all, why do we actually do maintenance and testing? Well, as we can see from the slide, in its purest form, maintenance has 3 primary objectives: to reduce the probability of failure, to restore the inherent level of equipment reliability. Now, what do we mean by that? There's been a long-held common misperception that somehow a higher level of reliability can be maintained into equipment, or a higher level than that was originally designed in. And that is simply untrue. It doesn't matter how much maintenance you do or how correct the maintenance is, the best you can hope for is that you will restore the original level of reliability that was inherent in the design in the first place. Can you improve reliability? Yes, of course you can, by modification. but not by simply applying maintenance. And we attempt to ensure that performance is not degraded by neither time nor usage. So for example, if you're going to overhaul a piece of large rotating plant, a pump, for example, a diesel generator, gas turbine, then the idea is that after the overhaul is complete, then the efficiency of the item should be fully restored. Now, there are differences to that. Certainly as plant gets very old, then yes, no matter how well you've maintained it, especially mechanical plant, rotating plant, there may be a fall off in overall efficiency. And whether or not money is spent to actually correct that, for instance, by replacement or not, is really an operational decision. So for example, for very old plant that is nearing the end of its life, it may be an operational decision whereby you simply live with the small degradation of efficiency, because the cost of replacement would not really give you a return on the investment, I think. Testing, and specifically testing of standby or redundant plant. No test, however successful it is, will guarantee that the item will work the next time it's called upon to do so. However, if all works well, every time we test something, a backup system, for example, it does provide confidence that the redundant systems will operate effectively when called upon to do so. And for most cases, we sincerely hope that will not happen. For example, emergency shutdown systems. We always hope we will never have to operate an emergency shutdown system in anger, but of course we have to test them periodically to give us some confidence that they will operate when called upon to do so. However, if we have a significant number of routine tests that actually don't work or throw up problems, then that in itself can prompt modification action to improve reliability based upon the operating experience gained. So the RCM process itself. Well, as you can see, it began in the US airline industries in the late 1960s. It's been developed across many industries over the decades since. There is an international standard. For those of you who aren't aware, SAE is the United States Society of Automotive Engineers. So as you can see there, although the RCM process was developed in the US airline industry, the actual recognized international standard is actually from the automotive industry. Okay? And the RCM process is really very, very simple, and it simply starts with the 7 questions are listed below, worked through in the order that they are listed. So really the RCM process is no more than a formalization, or if you like, providing a structure of what good engineers have been doing for many, many, many years. So first question is, what is the item supposed to do, and associated performance standards? Okay, so not only what is this function, but how well does it have to function? So for instance, you may say a pump is designed to pump water or whatever fluid is, but then you would say at this particular pressure, at that particular mass flow, at that particular temperature. Those performance criteria are really, really important to include in functionality. In what ways can it fail? What are the events that cause each failure? What are the mechanisms, if you like? And what happens, or what are the consequences of each failure? And in what way does each failure matter, if indeed it matters at all in terms of safety or reliable operations? For those items whereby failure does matter, then we ask, what preventive maintenance task can be performed proactively to prevent or diminish to a satisfactory degree the consequences of the failure? And the last question, of course, is what must be done if a suitable preventive maintenance task cannot be found? And that is normally correcting a design or modifying the plant. So applying RCM to optimize preventive maintenance for existing facilities. As you said, the original RCM process was intended to inform the design of airliners, primarily the Boeing 747. Now it's often an inherent part of design of facilities across many, many industries. And it is also often used across many industries with the purpose of reducing in-service failure, which adversely affect the bottom line. And that is perfectly acceptable to do so, because if we think about it, when facilities are brand new, much of the maintenance or the preventive maintenance is reliant upon the manufacturers, maintenance plans, their advised maintenance. However, as time goes on and a facility generates operating experience, then it can be the case, and it often is the case, that the original maintenance plans provided by the manufacturer can in fact be changed in terms of tasks and frequencies to optimize the effort required in the PM plan. However, when we look at RCM as a function of the design, it's normally a top-down functional approach as appropriate, i.e. you take the design, you break it down into its different kind of subsystems, into its various functions, and then you have a look at those functions in accordance with the 7 questions we saw in the previous slide. However, it's rarely suitable for in-service equipment, and this kind of forces a bottom-up hardware approach, i.e. systems and subsystems that are effectively analyzed on a component-by-component basis. And by that, I actually mean a team of engineers is often around a table with a large print piping an instrumentation diagram going through the system component by component, answering the 7 questions we saw on the previous slide. Unfortunately, one of the primary outcomes of doing so is that during the FMEA, when you're answering those questions, the failure effects of many components are found to be negligible in terms of adversely affecting production. But as you can see on the slide here, by then it's too late. The time, the cost, the effort of the analysis has already been incurred. However, what about a solution? One of the activities we can undertake that effectively precludes that wasted effort is to, before you begin the actual RCM analysis, undertake a process called critical component identification. Now, this a few years ago was developed by the Institute of Nuclear Power Operations, INPO, as part of their what they call AP913 equipment reliability process. And this can be readily applied to any given industry. It's not nuclear specific, I assure you. And it begins with a relatively simple process of identifying and categorizing components into these 4 levels of criticality, which we'll look at in more detail in a moment. And they're actually categorized against a set of predetermined criteria. Of course, that criteria will be industry specific, and it's usually performed by a single person as a desktop. Yes, there'll be a simple challenge process to check for accuracy, but it doesn't require a team of engineers. It requires a single trained person and can be done as a desktop exercise. So looking at the 4 categories, we have critical, and you can see there the failure of the component is intolerable and is likely to directly affect reliable production. There's an important thing to note here, that a subset of critical components are those categorized as what we call single point vulnerabilities, or SPVs. Now, the subject of single point vulnerabilities is probably adequate for a webinar all of its own. But just to give you an example, something like control valves, especially air-operated control valves, often critical in terms of production. So if you've got valves which are controlling the flow of 3 different chemicals into a reaction vessel, for example, it's obviously massively important to production that those flows are very accurately controlled. And of course, something like an air-operated control valve is often used because of the speed and efficiency with which it responds to changes in the required modulation of the valve. However, when we look at something like an air-operated control valve, from the programmable logic controller that is actually modulating the valve, from its actual actuator, its pneumatic or air supply, its the actual valve components. There are a whole host of things that can go wrong that will effectively cause the entire control function of the valve to actually fail at that point. So that's just an example of an SPV. Non-critical, okay, the failure of the component is tolerable, but it's simply more cost effective to conduct a preventive maintenance task than to allow the component to fully fail. That could be simply because of the downtime involved in repair, or it could be the actual cost of the spares. Okay? Low significance, the failure is tolerable, it's not considered worthwhile performing PM tasks. This is often, low significance is often referred to as run to failure. Okay, we haven't got an issue with this. Degradation will be detected by routine plant monitoring, and eventually it'll end up on the plan and it will be repaired. Not assessed are usually passive components whose failure would obviously have no adverse effect on production. A good example of that is something like a drain valve, where the drain valve is only opened to drain a vessel, for instance, for inspection. If the valve fails to open, they're normally manual valves, then all you've really got is a minor delay in getting the vessel drained and the inspection carried out. So when we look at the INPO AP913 streamlined process, we can see that we have the critical criteria feeding in at the top. We have the non-critical criteria feeding in later on. And effectively, most of, or many of those boxes you're looking at there are actually inputs of previously performed work, for instance, critical component identification, into the process. So it's no longer an integral part of the team-based RCM. It's predetermined criteria we're now looking at, which makes the whole process of RCM analysis much slicker and much more cost effective. So the actual critical component identification process itself, as you can see, is very, very simple and lends itself to a desktop exercise. It lists the components. Okay, what are the consequences of each component failure? Match that against the critical criteria, which we will come on to some examples in a short while, and just ascertain whether it falls into critical or non-critical, or indeed it ends up being low significance and therefore is a run to failure component, and the activities that you follow to identify whether or not, if it is critical, it's a single point vulnerability. So I did say we'd come on to some critical criteria. So I've picked some from UK Civil Nuclear, and I'm rather hoping that everyone will see just how simple a process this is. So these are predetermined criteria. So we said earlier that for critical, the failure of the component is intolerable to the facility and likely to directly affect reliable production. Well, there's the criteria against which the categorization of critical is measured. For example, an unplanned reactor trip, an unplanned control reactor shutdown, or a significant power transient or derating the reactor to greater than 100 megawatts electrical. Any one of those, reactor trip, shutdown, power transient, or derate, none of them are going to have a major safety consideration because the nuclear systems are designed to allow these things to happen safely, but they will cost a great deal of money. And with electricity generation, we are now talking into millions of euros, dollars, etc. If there's an unplanned entry into what we call a technical specification action condition requiring a shutdown equal to or less than 72 hours, or the immediate suspension of the handling and movement or transfer of radiated fuel, that again is not a safety consideration, but it's going to take an awful lot of money off the bottom line to recover from that. Any degradation of a critical safety function. Now, that doesn't mean that degradation of a critical safety function when it's called upon to operate. That's normally when you go and test a critical safety function, you found it's in a failed state or there's an issue with it, everything's fine, reactor's at power, yeah, there's no issues here, but the fact is you're going to have to actually spend quite a lot of money to make sure that that is corrected immediately. And any unplanned actuation of post-trip sequencing, effectively spurious actuation of safety systems that cause you to bring the reactor off unnecessarily. And it's the same thing with any unplanned reactor protection system. For non-critical, as you can imagine, it's less than 100 megawatts now, but greater than 5. So it's not going to cost quite as much money, but it's still going to be quite expensive. So the choice is, let's have a look and see if we can provide a preventive maintenance task, which will actually head off that failure, if you like, and bring you back to the 3 objectives of maintenance that we saw on the very first slide. And again, we've got loss of redundancy, or a likely health and safety and environmental or radiological reportable event. We're now obviously talking about near misses things. So any component whose failure may actually bring about a near miss, then that would be categorized as non-critical. And yes, we would look to apply preventive maintenance to try and reduce that probability of failure. As we mentioned earlier, touched on, if the cost of refurbishing or replacing the component is, kind of higher compared to performing the preventive maintenance task, then obviously it's the kind of cheaper option to perform the PM task. And in a similar way of the previous one, a loss of function of emergency response or emergency preparedness equipment, because these things cannot be tolerated for a lengthy period of time in case you need to bring them into use. Therefore, they would be classed as non-critical and they would be maintained accordingly. So, some illustrative examples from other industries. I've chosen 2 here, which kind of go hand in hand, train operators and rail infrastructure companies. So for critical, a failure resulting in unexpected cancellation of a main line train journey or a delay of more than 3 hours, because certainly in the UK, any delay more than 3 hours or cancellation, we have legislation which allows passengers to request compensation claims from a train operator. They're normally given in kind of vouchers for future free train journeys rather than trying to send actual money back to the claimant. For non-critical, a failure resulted in the unexpected cancellation of a local service. Now that would incur the cost of providing alternative road transport. Again, in the UK, the train company would be expected to immediately hire a series of coaches and allow the passengers to complete their journey by road. An expensive exercise in itself. For the rail infrastructure company, a signalling failure, for example, that results in the unexpected unavailability of a main line for a period of greater than 24 hours. That in itself would incur penalties from the train operators, who would probably have already been asked for compensation by the passengers. So that cost is going to be passed on. For non-critical, a failure resulting in unexpected requirement to undertake corrective action during quiet hours, deployment of nighttime maintenance crews. In the UK, I live about 70 meters from the West Coast main line, and you may be surprised at how many times nighttime maintenance crews are deployed to actually recover from problems that have happened either on the line or in the signals, and it all has a cost associated with it. So maintenance is the better option. For other industries, similar industry-specific criteria have been developed for many industries. Energy providers, retail, logistics, especially those providing just-in-time spares, manufacturing itself. So similar criteria can be really provided for any given industry with not too much time, cost and effort associated with it, thereby streamlining the RCM process and allowing that process to focus only on the plant, which is really important in terms of safe, reliable operations. So in conclusion, RCM really has attracted an unfair reputation of being time-consuming and expensive. Unfair because it's only in the case when adequate preparation has not preceded the analysis. As with many processes, if you target your efforts, you will normally achieve an improved cost benefit. I'll now hand you back to Steve, who's going to administer the Q&A sessions.
Okay, yeah, thanks very much, Dave. So we're open now for any questions. So if you'd like to type your questions into the Q&A function, we'll see if some come through there. But just whilst we're waiting for the first few to come through, yes, Dave. So let's think about so how much time and effort does it take to do this properly? So say that you've got a new. I mean, do you go about this for a whole new facility? At which stage of the design would you do it? You know, how long would it take? How much effort to do the critical component analysis, and then perhaps move on to the the deeper RCM task for the critical components?
That's a little variable depending upon the depth of the design for a new facility. But that would normally be done really as part of the design reviews. So that's not really any great additional effort in itself. In terms of actually looking at it, whether it's design or whether it's for an existing system, normally when you've got someone who's quite experienced, has gained some experience in doing this, you can normally do a fairly major system in a day or two, really. So for instance, at UK Nuclear Power Station, I would expect to do the entire diesel generator or the emergency diesel generator system, including all of its auxiliaries: fuel oil, lube oil, air cooling, air starts, protection electrical. I'd expect to do the entire thing in 2 days by one person as a desktop.
Okay, very good, thank you. We've got another question come through from Rajesh. Do we need to apportion for reliability in RCM? I'm not quite sure I understand the question. Can you think what that's getting at, Dave?
Yeah, I think so. And obviously the gentleman can come back at this if I've misunderstood. In terms of detailed reliability claims, for example, QRA or PSA claims, they're not strictly speaking part of the RCM process, because the RCM process simply deals with what we call probable failure modes. So for example, the FMEA supporting the RCM process would be significantly different from the FMEA supporting a PSA or a QRA. In the second case, yes, the reliability data is very much a component of that process. Whereas for the RCM, we only look at what we call probable failure modes. If you like, we look at the usual suspects. So if we're looking at a horizontal pump, we know that the pump shaft will wear. We know the impeller will wear. We know the bearings will wear. So we will simply look at the maintenance required to kind of slow down that wear, or kind of reduce the probability of it failing, without really looking specifically at the actual reliability data, as it were. I hope that's answered the question adequately.
Okay, thanks, Dave. There's a follow-up from Rajesh. Here he's referring to a railway metro, and specifically, how would we go about doing an RCM for the track infrastructure and the stations?
Right, okay. What you would actually do is simply take each of those aspects of the metro, in isolation to an extent. Well, initially in isolation, they're going to come together at some point, and then you would actually simply, and I mean simply, break it down into its various subsystems. So for the station, you could be looking at how the passengers move about. You could be looking at lighting, communications equipment, all of the kind of the physical aspects, and take each of those subsystems in turn, and then actually do the critical component identification for each system, and then apply the RCM. Likewise for the track infrastructure, because obviously we're dealing with a metro now, so we're also dealing with the, if you like, the civil or structural aspects of the tunneling system, and all of the signaling, etc. And included in that would be emergency escape routes, for example. That would be a subsystem all of its own. You would again do the critical components identification, identify your critical components, including your SPVs, your non-critical, and then push those through the RCM analysis to ascertain the appropriate preventive maintenance regime for those. Again, I hope I've answered that question adequately.
Okay, thanks, Dave. I think it's kind of a related question, really, from Mahanad. Does RCM cover all the fields, including different equipment? And he's saying, for example, if you take an oil and gas field, a large infrastructure, and particularly offshore, then you've got lots of categories of plant. So, for example, you might have a semi-submersible drilling rig, a drill ship, a jack-up, a fixed-leg jack-up platform. Does RCM cover all of those different types?
Absolutely. And just to kind of widen that response a little bit, certainly in oil and gas just like most industries, if we think about it, most of the components are not necessarily specifically designed for that industry. Pumps are fairly generic, valves are generic. Yes, of course, the oil and gas, you do have some specific components in terms of well completions, in terms of formation isolation valves, packers, etc., which are indeed industry specific. They're not used anywhere else other than in drilling, I think. But for the vast majority of the plant, it's made up of pretty generic type components by all means. And as you break the systems down into subsystems, down into assemblies, then it's no different in that respect from any other industry once you're applying the critical component identification.
Okay, thanks, Dave. Good question from Steve. Is condition-based monitoring the way ahead, as equipment failure can be anticipated and the defects that can be introduced by conducting planned maintenance eliminated?
Yes, is the short answer, with a caveat that it depends upon the operating context of the component. For example, if Steve would like to get in touch with me at some point, I'd draw his attention to a particular system, say at Hunterston B nuclear power station, whereby in the water treatment plant, every pump, duty and standby pump that's in that treatment plant can in fact be commonned, because the duty pump is nearly always running. As long as you routinely change over to standby, you can common those as well. But there are two pumps there, which are what you call the emergency makeup pumps, that to actually start those, the run, for instance, the vibration monitoring, during normal operation would push such a slug of water forward into the system, it would trip out all of the feed heaters, it would flood them all out, and thereby you'd probably be pulling your reactor power down eventually by about 11 to 20 megawatts and lose a lot of money. So because of the operating context of those pumps, there's no recirc line to start them back to their water supply. You can't really run them to conmon them. So on that particular occasion, you revert back to traditional teardown, inspection and overhaul. I hope that's answered Steve's question. But again, get in touch with me, after this, and I'd be only too happy to discuss further with anyone who chooses to do so. Okay,
thank you. Question from Mahmood. Can we consider failures happening because of power? Let me rephrase that. Are failures that happen due to power failure critical?
That rather depends upon the availability of backup systems. Primarily, the answer to the question is normally yes, because you really do not want to have an over-reliance upon emergency power generation. So for instance, at a power station, the connections to the grid are vitally important, because yeah, you can say, well, if you lose the grid, then you've got your emergency diesel generators. But of course, if you lose the grid, the first thing that happens is the reactor trips, which is a huge loss of production. So the emergency diesel generators are simply there to actually keep the post-trip cooling and keeping the fuel cool. Then you are no longer in ability to generate electricity until you're recovered. So if those grid connections were inherently unreliable, yes, you would indeed regard those as critical, not just in terms of safety, but in terms of lost production.
Okay, thank you. Another question from Mahanad. Okay, so what's the difference between RCM and JD Edward? I don't know if you're familiar with JD Edwards, but I think that's a maintenance management software, like sort of Maximo, Dave.
Right, okay.
So what's the difference between RCM and a maintenance management system for completing the preventive maintenance for all equipment? It looks the same to me, says Mohammed.
You see, yeah, the things, you know, like Maximo or any kind of asset management system, so for instance, EPRI RCM Workbench, these are just tools for the recording of the RCM analysis. The RCM analysis is performed by human beings. It requires the human brain, and it requires the knowledge of human beings on the functionality of the plant, which, for instance, why any RCM analysis, it would be hugely important to have both operations and maintenance involved. Operators are very skilled normally at determining the consequence of a failure of any plant item, whereas maintainers are very good at identifying the causes of such failure. I think so. It's really important. It's also really important to get work planning involved, because when you embark on any RCM study, the first question, when I'm asked to do it, the first question I always go and ask the facility is, how do you intend to implement this? How can I present this analysis in the most efficient manner possible so you can enter it onto your Maximo or your JD Edwards, you know, whatever your asset management system is. So these are just systems for recording the results of the analysis. The analysis is still performed by a human being. RCM is not automated in that respect.
Okay, a question from John. Thank you, David. This is really interesting. I see significant alignment between the RCM process with its 7 questions and a bow tie analysis taken to a very detailed level. And I think what he's referring to there, we have a barrier against a threat or a mitigation event against a consequence, and we can sort of drill down to what do we need to do to make sure that barrier is working. What I'm not sure of is how criticality is determined within the 2 processes. I'd appreciate any comments you may have about your view of the similarities.
Right, okay. Certainly in RCM, the criticality, as you can see, is determined against that you know, specific list of criteria, which is, you know, unashamedly aimed at protecting reliable production, I think, rather than safety. In fact, if we think about single point vulnerabilities, certainly in the UK, because of the goal setting or a LARP-based UK legislation for determining safety cases, I think a single point vulnerability effectively cannot exist in a safety system, because all safety systems in the UK under the LARP process must comply with what we call the single failure criterion, i.e. no single failure can take out the entire safety function. So an SPV can't really exist in those circumstances. So SPVs only really exist in production plant, if you like, often called a balancer plant, I think. And another thing to be very, very, it's very much worth noting is that there is one major caveat with RCM, and that is RCM, when you're performing an FMEA, it is focused entirely upon equipment failure. And what that really means is when you assign a preventive maintenance task at the appropriate frequency, the RCM process will effectively take the view that that task will be performed correctly. It does not take into account human error, because that type of process cannot legislate for human error as you can in a bow tie thing. Like I said, the RCM process will actually simply take the view that if a maintenance task is assigned, it is logistically and technically feasible and it will be performed correctly. The maintenance teams will do exactly what they're expected to do. I hope that kind of helps. But again, come back to me. You've got my email address. I'd be only too happy to talk to you in greater detail.
Okay, thanks, Dave. There's no more questions coming through, so we're up to 40 minutes. So I think we'll wrap up now. What we will do is make a recording available to everybody, hopefully within a sort of 24 hours. And when you leave the webinar, you should automatically receive a survey in your browser. It will literally take you, 10, 15 seconds to complete that. We really do appreciate your feedback, especially if you can identify any topics that you'd be interested to hear about for future webinars. I mean, what we want to do is, provide topics that you find interesting. So just let us know what you'd like to hear. And as Dave said, if you've got any questions, any technical questions arising from the webinar today, you can get in contact with Dave directly. His email was at the start. You can get it all. We can find it through the company. There's a couple of email addresses up there. Or you can just go to our website, and there's a ton of forms on there where you can just sort of fill in, and we'll get back to you. So thank you, Dave. Once again, thank you, everybody else, for your attention. Really grateful. You take your time out of your day to listen in to our webinars. The next one is on Thursday, same time, same place. And we're looking at risk-based inspection of hydrocarbon containing equipment. So look forward to that. Hopefully you can join us for that one too. So in the meantime, please stay safe, stay secure, enjoy the rest of your day. Thank you. Goodbye.